Welcome back to another HVAC Engineering Techie training video. Today's training video is on critical electrical power systems. This is a systems video, explains systems and what they are and their components and how they operate. So it can help you when you're doing other things that are more critical in your discipline. But this is how critical electrical systems work. So thank you very much for watching the video. I really appreciate it. I appreciate you being a subscribing member. If you're not, I'd really like you to become one. All you have to do is hit that subscribe button down below. Give me a thumbs up if you like the video. It's absolutely free. No one will ever bug you. And the reason is Google uses that data to evaluate my video, which keeps me on the air. Don't forget, HVAC Engineering-Techie is a channel that talks all things about technical building systems, including design, construction, controls, test and balance, HVAC, of course, electrical, plumbing, fire alarm, all the systems, technical systems in a building. So let's get started. I'm talking about critical electrical power systems. So to get started, we'll review all the electrical associated videos we have in the training videos. Just so you'll get an idea what's out there. D10 electrical system design, and that's actually for non-electrical engineers. It's a light version of electrical design. D11 electrical lighting design, again a light version. S12 electrical motors, drives and systems. S50 basic electrical, basic for commissioners or technicians. S51 electrical power distribution systems. S52 critical electrical power systems, which is this video. We'll explain what critical systems actually are. S53 is electrical lighting systems. S54 is electrical safety. CX9 is the technical commissioning of electrical systems, part 1, and CX10, which is a technical commissioning, part 2. Part 1 basically is all the pre-site stuff and all the startup paperwork, and CX10 is basically functional testing, where we actually prove the system is functional. So hopefully those will be helpful for you. So critical electrical systems. So a critical electrical system are electrical systems that are essential for the operation of the facility functions that cannot have interruption in electrical power or quality of power, such as healthcare facilities, data centers, or critical manufacturing processes. These systems must remain operational during power outage to prevent life-threatening conditions, data corruption, and electrical mechanical system crashes. So that's pretty simple, that they're just systems that can't go down. Well, it's pretty hard to have a system that doesn't go down if you think about it. And what this is all about basically is getting rid of any single point of failures so that you don't have one thing taking the system down. So, and of course, pay attention that we don't have any cascading failures also. So this is hospital and medical facilities, data centers, computer processing centers, critical manufacturing facilities, banking centers, communication switching centers, electrical components that are critical as more than one source of power. That's critical, and it's in case a utility has a transformer go down at a substation, you need to have a separate substation feeding a different source of power so that doesn't happen. Standby power and short-term backup, redundant power distribution, and it can have many more things, and we'll talk about them as we go. So the critical components of the system is electrical switchgear, of course, generators, generator switchgear, automatic transfer switches, and UPS systems and UPS switchgear. So it's anything that's associated with those critical systems that provide the electrical power to those critical systems. So system switchgear, you can have protected or separated from other facility sections. So in other words, you don't want the critical facility being fed right out of the same gear that everything else is fed out of. They come into the SES, and in the critical system, all their switchgear is separated out past the SES. So redundant utility feeds, fault tolerant, meaning they don't have any faults going on. They're normally dedicated equipment rooms for just the critical needs. This happens to be an idea of what we're talking about here. Now, this is the main transformer coming in. This is power feed A. This is the utility switchgear, which is our SES. And then we have a generator coming online that feeds these ATSs, which feeds the UPS to the critical output loads. and it may feed the mechanical switchgear that feeds the mechanical systems, because the mechanical systems are also important to the criticality of the facility. So not only do you need to have the electrical system up all the time, but you need to have the mechanical system up all the time, because if the mechanical goes down, the electrical will not, the critical data center or whatever will not stay up, so it has to be. So these can have a N+1, which we call it. So N is described as a full load. So if you have an N load, you have the full load, and then do you need N+1, which means you have a full standby. This one shows it as an option. It can have a generator, and it can have a standby generator if you need that also. So even within this tier level, you can have different levels of redundancy within the tier level. So critical system generators, natural gas, fuel oil, or dual fuel. Interior units can have big interior units like this. You can have small units outside with belly tanks, where the fuel oil is put in the belly tank. It feeds the generator. These are probably gas-fired, might be dual fuel. So we can have interior units, can have exterior units. Interior units are probably preferred in real cold climates where you have a lot of snow and ice. And then maybe the warmer climates, we can put them outside. Battery units, you can have battery units. We can have very large interior units. This is a pretty big backup power system because these are very large generators. And you can have large outdoor ones also, and they're normally multiple done together. And these are all for critical systems, of course. Fuel storage systems. So normally you can have belly tanks like this one, and have a day tank, which feeds the generator. And you can have above ground storage tanks, and you can have below ground storage tanks. So it depends on how much fuel you need to store and how long you think you need to run if a power outage. So we also, here's what a typical system looks like with an underground storage tank that feeds a day tank like this. And the day tank feeds the generator. So the generator has its pumps that suck out of the tank. And we have return lines going back to the day tank. And the day tank itself also has pumps either in the tank or out here on the tank that feed the fuel from the tank back into the day tank. So there's fuel always rotating in and out. This is a real typical system you'll see all the time. So generator paralleling switchgear. Now, paralleling switchgear controls multiple generators and allows the generator to come online and parallel with the existing power feed. It's really important because the frequencies have to match. So this gear is very critical to bring it on quickly and to bring it on at the right frequency. Parallel loads and frequency. And basically all it's doing is it's like switch gear. And it's controlling, if you have multiple generators, it'll control those generators. So what it does is it brings one up. And if the load is greater, it'll start more than one. And they start up and level out and carry the load, and it'll vary the load between the generators as required. And the paralleling gear will do that. Many times the generators have their own paralleling gear built in them, and they just communicate cross generators. But on really large facilities, they still use generator switchgear, paralleling gear. Standalone switches, we have ATS system switches. And this basically is what happens is when you lose normal power, this switch immediately disconnects from normal power and switches to emergency power. And it makes sure the generator starts. Once the generator is up to voltage, then it switches the load. So that's part of the thing we worry about in the design and testing of these systems is how fast the generators come up and get to correct voltage and are able to accept the load. The other thing we have to deal with is how you schedule these switches to switch over. If you switch everything at one time, you might have a problem. So they can do it. This is a small cabinet-mounted ATS switch. This is a floor-mounted standalone ATS switch. And then we have whole pieces of switchgear systems that have an ATS that switch the whole system over. And then our breakers that are in the system all switch when this ATS switches it over. So this is a bigger system alternative. Small standalone units for UPSs, and UPSs, of course, are uninterruptible power supplies. And what they do is they have battery backup, and they're continually feeding power to the equipment from the batteries when it's no power. But when there is power, sometimes, and you can have two kinds of UPSs. You can have a standalone standby UPS that only comes on and takes over power when they lose the power feed. Or you can have others that actually condition the power, so they're always feeding the power through their rectifiers to make sure it's absolutely clean power. And you can have either one, but either one takes over when there's a power failure and keeps the units up. And you can have UPSs like this as an enclosed system, like a small one you'd have on a small computer system. And this is a bigger unit that has batteries in these battery racks back here, and this could take care of a small computer room. And these are rack-mounted UPSs, large UPS units with separate battery packs. We have units that are just the UPS, and then the battery racks are either in cabinets like this one. This one has a cabinet here, or else be like this one, where the batteries are all remote. So it depends on how big a one you have. And then, of course, we have some that have entire rooms full of batteries, and the UPSs are in separate rooms that feed these units. So they're all sizes, but they're basically UPSs are very, very important to critical power systems. So fault-tolerant infrastructure systems. Fault-tolerant means no or few single points of failure depending upon the desired uptime. How much uptime do you want? So redundant electrical feeds, redundant cooling pipe systems, redundant water supply for mechanical systems, redundant control systems, hot standby, redundant control and communication systems. So in other words, if you're going to have a room that needs to be up all the time for electrical, you need to worry about the electrical, but you also need to worry about everything else that feeds that room, including mechanical, any water surfaces it needs, and make sure it has redundancy in those systems and the control systems. So it becomes quite integrated pretty soon when you get down to it, and you're trying to have the controls are all fed from different sources and are redundant, totally redundant. So if that's the case, then there's a lot of things to pay attention to. So this is a critical system tier architecture as defined by the Uptime Institute. Now this one's a little old. This may be 4 or 5 years old, so it may be a little outdated, but it's probably still all the same. This is the tier number. It goes from 1, 2, 3, and 4 tiers. And where tier 1 is a real simple data room, something that you want to make sure it doesn't power fail, but it's not super critical. 2 is a system that's a little bigger, maybe a little data center in a building. And tier 3 is a large critical power system, and tier 4 is a very serious power system. And the real critical part here is the uptime. If you look here, this is 99.67, 99.75, 99.98, and 99.9999. This one can only be down less than 0.8 hours a year. This one's 1.6 is 22, and this is 28 hours a year. Now, 0.8 hours may seem, well, that's kind of a lot, but that's total. So it means if you're down for 2 seconds, then you're down for 2 seconds. So these are designed to be up a lot. Now you can see that the cost, and I'll show you in a second, the cost goes exponentially higher over here. So the redundancy component here is just N, which means it's designed to carry the load. Tier 2 is N plus 1, so you have redundancy. And so tier 3 is N plus 1, and tier 4 maybe 2 or 3, N plus 2 or 3. So this could be a lot. Distribution pass, 1. Tier 2 is 1. Tier 3 has 1 normal and 1 standby alternative, but Tier 4 has redundant. Yes, they're both active. Fault tolerant, Tier 4 is yes. Maximum site availability, that's the one I just talked about, and the downtime. And here you can see that what kind of building can this go in? This could be a tenant or a room inside a building. These have to, 3 and 4 have to be standalone buildings. You can't have any other building occupancy in that space. You can have a data center with a small office in it for the technicians of the data center, but you can't have any other occupancy in there. And staffing, Tier 1 is none. That's just a little UPS or something for your room. And Tier 2 has 1 shift, 1 person per shift, just 1 shift. Tier 3 is 1 plus shifts. So this one actually you have more than 1 shift. This one is 24 by forever. This is 24/7. So it's forever. You have people on staff. Load design, 100%, 100%. Tier 3 is this system has to be 110% of the load. So not just N, but it has to be larger than N, and this one has to be larger than N. Gross watts per square foot, 20 to 30, 40 to 50, 100 to 150, 150. Now, this may not be adequate. Now, this may be one of the things that's out of date because the data center industry has changed so quickly that it may be, these need to be upped a little bit. I'm not sure about that because what happens is the processors get capable, more and more capable. They actually do more work for less watts, but they take up the same space as before. So I'm not sure, but I think the watts probably will need to be updated. Uninterruptible cooling? No, tier 2, but tier 3 maybe. Tier 4 absolutely yes. So raised floor height 12 inches, 18 inches, 30 to 36. Tier 4 30 to 36. Utility voltage 208 to 480, 208 to 480. Tier 3 12 to 15,000 volts, and the same for Tier 4. Now this cost, I'm sure, is changed. Even this has been updated, probably 2 or 3 years old. So the raised floor cost plus the raised floor plus the UPS. So you have to add both these together. So the room itself should cost you about $470 a square foot. Everything else should cost you about $21,000 a kW. In Tier 2, the $470 per square foot plus $23,500 per kW. Tier 3 is still $470 a square foot, $42,800 a square foot. Now, this square foot cost will probably change because the floor heights have gone up, but not much. And then the Tier 4 is still $470 a square foot plus $48,000 a kW. And these are the numbers I'm not real sure about where there's at. The building costs will have general inflation applied to it, but this other probably not. This is a lot of other things. It's actually the cost of the gear in the electrical gear, so it could be a problem. Now, none of this includes the actual processors in the room. This is just the utilities for the room and the room itself. All right, so let's talk about tiers. This is Tier 1, and you remember what we said Tier 1 was. So it has a power feed coming into the switchgear. It has a generator, backs it up, and has ATS switches. It has a UPS output to the PDUs, as to the computers. And it doesn't have standby, but it has that capability. And then we have an ATS going to the critical mechanical systems. So this system is backed up by a generator, basically what it means. It provides basic capacity without redundancy. Expected uptime is 99.67% annually with a potential off time of 28.8 hours. Suitable for small business owners who prefer independent IT systems without relying on general building infrastructure. So this is all special infrastructure. I mean, it's still coming in from the utility. If the utility uses power, at least he can go on generator to have his system up. This is Tier 2. You can see Tier 2 comes in from one power feed. It has utility switchgear, and then it has ATS and generators, and it has capability of redundant generators. This is optional, but it gives you that N+1. And these ATSs switch to the UPSs, and then you also have the option of a redundant UPS. So this is a little more critical to you. You can have redundant UPSs, so if you have a UPS problem, you can switch to the redundant one. And then it has mechanical switchgear like the other one. Redundancy in critical power and cooling components. Non-redundant distribution paths. Expected uptime is 99.75% annual with a potential off time of 22 hours. Ideal for small to medium business owners seeking enhanced protection for their IT systems. You can see it's getting a little more pricey as we go up. And this is that Tier 3. Now this is the first one that requires redundant power feeds. We have a power feed from the utility A, and we have a power system B from the utility. And then we have the utility switchgear for each. And then we have a switchgear for a generator. And this can have redundant generators, but it'll have it'll have an end generator, but if the load's too large, it may have more than one generator to cover the end load. And it can have redundant end loads. So let's say it takes 2 generators to carry the end load, and you want redundancy, you can use 3. So that can be a benefit there. You have the ATSs going to the UPSs. Still, you have an option for a redundant UPS. And then you have the switches going over to mechanical switchgear. But what's different is you have the same thing on this side. So this side can feed the critical systems and the mechanical systems, and this side can feed the mechanical systems. So what happens is if A is the normal one that's on, it will be on A. If it has a failure, then everything switches over between the switch gears to side B utility. So the system never sees a power outage. It actually is transferred immediately to the other side. So this is a general layout for this, and this is comprehensive redundancy for power, cooling components, and distribution paths. High uptime expectancies of 99.98%, uptime with a potential offline of only 1.6 hours. Ideal for medium to large businesses seeking protection from IT system disruptions, especially during maintenance or switching of distribution paths. So this is one that is automatic transfers is pretty robust. Now here's the top dog, Tier 4. And it's the same as Tier 3, except it has redundant everything. So we have generators for power feed A. We also have redundant generators for power B. We can have N+1 if we need it. We think so. The thing is different that these switch gears are actually connected through a automatic switch, so that if this guy goes down, it is automatically connected to the other side. And you can see these all have that. So this critical system has redundancy. It has more than likely more than one redundancy. It probably has two level of redundancy. And everything's separate path. This is as extensive as we know how to do. We could probably get a little crazier if we had to, but mainly this is a really, really exotic data center system. It's fault tolerant, so it's fault tolerant. You can't have a fault here. I mean, if one thing faults, it can switch over to the standby side, and it won't be a problem. Exceptional uptime. Tier 4 data centers aim for an expected uptime of 99.999%. Maximum 0.8 hours downtime. Ideal for large, complex businesses seeking the most stringent protection against disruption for critical operations. So this is a Tier 4 system, which is the one. And you can see the mechanicals N+1. And the support is also N+1. So all of this has, not only do we have the whole inside, but we have N+1 everywhere, totally fault tolerant. So that's an exceptional system. This is the top one. So critical verifications items that we need to verify when we either commission a system or start it up, or we check a design. We need the load capacity is at N+1 or N+2, and then we need to check the design to make sure it meets those criteria. Dual main feed, standby feed, generator feed load N+1 or N+2 for the feeds. Backup UPS system, power capacity, redundancy, and location. Cold aisle, hot aisle, or in-rack cooling, that we have the distribution within the room correct. Location of crack units, no latent cooling, remember that. Compartmentalization for everything, so that we have everything compartmentalized, so if we have a problem in one area, it's not going to affect another area. And what that means is, if you have a switchgear room, you need to have a separate switchgear room for the redundant side, because if you have a breaker blow up, and one of them is going to take that room down, so you have to have the other one available to do that. Maximum underfloor height and underfloor ceiling. Now this may have changed a little bit, because when I got the tier ratings from the Uptime Institute, we were heavily into data cable. And the reason the floor height raises is because there's so much cable underneath the floor, it restricts the airflow, because the crack units normally flow to the computers under the floor. Well, nowadays we're using mostly fiber, and a lot of them, that fiber is above the units, not below floor. So they may reduce the floor area if they don't have any cabling down there. But I'm not sure about that. That would have to see what's currently in the industry. Prime cooling capacity, N or N+1, and redundancy. Redundant domestic water supply, cooling towers, they absolutely have to have that. Cooling towers use a whole bunch of water, and you can't be down. So in other words, you have to have a redundant water line from some other source of main. And that's a little bit more difficult than it is electrical, because electrical understand that they need it coming from a different substation. But water companies, where you need it coming from a water main that can't, if you shut this water main down, it won't affect this main. That's a little more hard to figure it out. It's not hard to do, but it's hard to figure it out because the documentation is not quite the same as in the electrical utility field. Fire protection system compartmentalization. So when you go through the fire protection sessions, you'll understand that these critical systems normally have two fire protection systems. One is a gas system to protect the data, and another one to protect the structure. A sprinkler system to protect the structure. If the structure is getting ready to burn down, it's way too late for the data. So you can pour water on it, not a problem. Fire alarm, emergency shut-off switches, EPOs, and a recovery plan. An EPO is an emergency turn-off switch. So if you hit it, you turn off the systems. But what's critical is how you recover from that EPO event. It's not a simple fact how you get everything back online or restart it after an EPO. So we need to have a recovery plan for that. That's really important. Redundant power feeds, redundant chill water lines, pumps, etc. Battery location, redundancy, and compartmentalization. Verify maintainability without load interruption. So can you maintain everything? If you have to turn something off, then it has to have redundancy. So the redundant side can be operating. No single point of failure. That's the key thing. No single point of failure. And you have to look really deep to make sure. Because control systems can be a single point of failure. So you got to make sure you have a fault-tolerant control system, which is not an easy thing to do. Well, that was critical power systems. I hope that was helpful. A lot of this work going on right now, so I'm sure you're going to encounter this. I thank you very much for watching the video. Thank you guys for being here. If you have any questions, drop them in the comments. I get to them every couple of weeks. Appreciate it. Thanks again for watching the video, and I'll catch you on the next one.